Hi, welcome back. We spoke last time about macromolecular crowding, and I introduced to you some experimental data that provides us evidence that macromolecular crowding exists, that it affects rate constants, and that it adds up back to the theory that we had discussed in last week's journal analysis. This picture again from there to remind you that macromolecular crowding is kind of important and it is interesting to study it. But once we go from experiments and descriptions and numbers that we, quantitative measurements that we obtain from experiments, then it is obvious that we need theory to make more sense of it. And so for today, I'm going to cover a whole bunch of topics which I'm going to do in two parts. I'm going to start with discussing a solution for the probability of binding with crowd-instant ligand receptor systems, move on to osmotic pressure and the role of crowding in it, excluded volume interactions, entropic ordering, self-avoiding walks and protein folding, diffusion and crowding environment. So we're going to talk about the first three parts first and then the second after that. So of course, we, as I had alluded to yesterday, very nicely can go back to the formalism that we had discussed last semester in using the statistical mechanics engine for understanding statistical distributions, multiplicities of probability of being bound or not bound, and then adding in the additional component of crowding. So what we are looking at here is ligand receptor binding with L as the number of ligands, R as the number of receptors, and omega as the number of boxes. This is the lattice model that we are used to from earlier. Yes, lattice gas model. And indeed, what you observe here is, of course, that one of these is the bound state, right? While all these are free ligands and bound. And knowing this, we had last time used this idea that you have multiple microstates, you have a sum over average, and if you want to know how likely one state is as a representation of all, you need to go through the statistics of it and put together a probability. And this is also true not just of the DNA that I just showed you earlier, but also of the ion channel microstates, where closed and open can be considered to be the two states and the dynamics intermediate between them. This paper from Keller is a very nice elucidation of this problem for those of you who are fascinated by neurobiology. You might want to go back and look at this one, because it essentially describes the biophysical basis of fundamental neurobiological phenomenon. This is electrical conduction through ions. But anyway, we come back to our states and weights for binding. And if you remember, we said that the energy associated with the soluble phase of the ligand is epsilon sol, multiplied by L gives us the total energy of that state, and then L minus one molecule being bound into epsilon sol plus EB for the bound state. That is to say the whole system, right? That's what we're really trying to describe. That goes into these equations respectively. And the multiplicity then, and this is again your based on your combinations, preventing overcounting, meaning to say two arrangements where the things are the same are removed. Therefore, omega, that is the number of boxes, upon L factorial upon omega minus L factorial, which simplifies to omega to the power L upon L factorial, gives us how many various ways of arranging it in this way are possible. And this then for the ligand bound state is given by omega L minus 1 upon L minus 1 factorial. The weights, therefore, become the Boltzmann's probability, that is e to the power minus 1 by kBt into the energy, right? And in the prefactor comes the multiplicity that we usually then call Z, yeah, the Zustandssumme. All right, some overall states. So essentially, this is back to our old construction, so there's nothing new here. And if we want to look at the probability, then it's just simply the bound states summed divided by both bound and unbound states. I mean, this is kind of obvious that this binding probability, then as we discussed last time, is a true probability, goes from 0 to 1, and has very nice properties of summation and so on. Now, when we look at the binding kinetics with a ligand concentration, we see a curve that looks like this, where as the difference between the bound and unbound state increases, we get a more dramatic probability of binding, with the delta epsilon, that is the difference between the two states, being the key determinant of the likelihood of a reaction. And this is expressed in bulk kinetics in biochemical terms as the dissociation constant, which is lower. And you remember that in your ligand receptor binding, or two molecules associating with each other, let us say two proteins associating with each other, or a DNA and a protein, or a chemoattractant and a receptor, or a drug and a target molecule, that the lower the KD, the more strong the binding. And this, again, in the light of drug discovery, and we're in the middle of a medical emergency, and all the science should point towards more development of antivirals. But if you're trying to build a better antiviral, you want a lower KD, for instance, right? And that is related to the difference in energy, free energy, between the free and bound state, right? And you're aware of this, right? But what happens when, in this lattice model of ligand receptor binding, we now add some item called C, which is the number of crowding molecules. And these, in our lattice gas model, occupy lattice sites like this here, preventing the ligand from occupying them. This is like back to our local train. When the train is already full, you're not going to be able to enter. Or if it is half full, chances you're standing are higher. Chances that you even move around much, or in some senses, your degrees of mobility are reduced. And this is coming to, if you remember our old discussions about entropy, osmotic pressure in the osmotic engine thought experiment, and a lot of other paradigms that we have been discussing repeatedly in this course. So in that sense, that's not very surprising that you should expect that the presence of a crowding molecule should change something in your system. In fact, what it does is that it changes the ligand receptor binding probability to an expression that now includes this minus sign here, which is the concentration of the crowdin, so number of crowdin molecules in the lattice with omega sites, and your delta epsilon L, the energy difference of bound to free ligand, while it remains the same, it is multiplied by a prefactor that is reduced by C. As always, we are talking about the dilute limit. L is much less than omega. And when C increases, and this is the important thing, when C increases, we expect from the theory that P bound will also increase. In other words, increasing the crowdin concentration increases the probability of binding. So just think about this equation for a bit, look at it. Some of you enjoy Python, plot it, and we will go and see what people have done, both theoretically and experimentally. Turns out that when you plug this into an arithmetic, I mean, you just graph the equation essentially, P bound as a function of number of ligand molecules, you find that with increasing ligand molecules, your curve becomes sharper and sharper. And please remember, I mentioned to you something like your half maximum, or whatever you want to call it, decay constant, how fast the curve goes from 0 to saturation. Well, you see this here visibly, and I just want to point it out to you. This is 0.9, 0.45 is its half max, Vmax half. That is somewhere here at 10. So this one is at 10. This one goes up over here, so 0.92, so still 0.45. So this one goes at 5 probably, and this one saturates also at a higher value, and its half maximum 0.95 is point something like slightly higher, and it's even smaller, it's 1. In other words, the half maximal value of saturation of bound state decreases further and further as a function of increasing crowding, consistent with our theory. What about experiments? Well, when you measure the ATPase rate with increasing peg concentration, as we had shown earlier in terms of the T4 bacteriophage virus DNA clamp loader protein G4462P, then with increasing crowding concentration from 0 to 7.5% weight by volume of polyethylene glycol, you see that the rate or the velocity of reaction, which is a readout in some senses, a surrogate for the probability of being bound, because the reaction will not happen if the substrate enzyme are not bound, also increases successively in a qualitatively identical manner. I mean, that's really striking. And these fit curves, these lines, are indeed based on the model. In addition, by doing a little bit of arithmetic, you can show that the KD, the dissociation constant, which is something that we always want to measure in binding or an unbinding reaction, scales as a function of 1 by V, where V is the volume of a single lattice site, which is the characteristic size of the molecule, let us say the crowdant, into e to the power beta delta E. And delta E is again the difference between the bound and the free states of energies, beta being 1 by kBt, your scaling constant. So this also implies that Kd with a crowdant in place upon Kd without a crowdant, yeah, meaning the ratio of the two decreases further and further with phi c. What is phi c? Is nothing but volume occupied by C upon total volume of the system. This is also then referred to as the volume fraction. In literature of packing and so on, it is also called packing fraction. Now, this also means that binding constant can be peg dependent. Again, T4 ATPase data, peg size of 12 kDa, protein size is much greater, 164 kDa, omega large boxes, R small boxes in each box. So now we have a model that is a bit more precise, where our crowding molecules relative sizes, we said from this, should be about 1/10 of the size of the protein based on the Dalton mass alone. And so we say, for simplicity over here, it is some half or 1/4, I'm sorry. We can make it much smaller actually. For our calculation purposes, this is what we take. Small boxes of crowdant and middle boxes are ligand, and the largest boxes are receptors. Then in such a case, considering the relative size asymmetry also, we have the probability of binding now becoming 1 plus omega by L, 1 minus phi c. Phi c is the volume fraction of crowding, which, since we're talking in terms of number of boxes, is just simply C boxes upon R times omega boxes, the total number of boxes of the characteristic size of the smallest molecule R, right? Um, this is again assuming L is much less than omega, and n plus R factorial upon n is approximately equal to n to the power R. This is the simplification that we get. It turns out that the KD also changes with the volume fraction, in the sense that KD phi C upon KD phi C, where there is no crowding, is equal then to 1 minus phi C to the power R. In other words, the ratio of the dissociation constant scales with the volume fraction of crowding to the power R, which is our relative size of the molecules, where R small boxes in each large box are indicative of the number of smallest elements of the system, right? So it's, if you could say, it is the multiplication factor telling us the relative size ratio between the crowding molecule and the largest ligand molecule. Yeah, because the largest ligand molecule is determining the omega. And so knowing this factor, that is 4 to 1, we are basically multiplying it by 4 in this concrete example. So I hope that is kind of clear. And so we, in fact, can say that in addition to relative sizes, crowding presence, other factors also may affect crowding, which may relate to lattice positions and half positions, meaning to say the ligand could be half between two boxes, the receptor could be between multiple boxes and junctional points. But by and large, we find that the error in this methodology is minimal compared to these kind of errors. It refines the answer, it is true. So to move on to the next topic in the effect of crowding, we will talk now about osmotic pressure and how crowding affects it. So the osmotic pressure due to excess hemoglobin has been found by experimental optimization and merging with theory to be P, which is the pressure, is minus kVt upon V, volume of a single box in a lattice, multiplied by the natural log of 1 minus the concentration, in this case of hemoglobin molecules, in a given volume. Now, H concentration is basically the number of molecules times omega into V in the denominator, V being the smallest volume of whatever the smallest element of the system is. This is saying that as excess hemoglobin is increased, we will see that the pressure of the osmotic pressure of the system will increase, and the dots are lattice gas model. That is the one that we've been working on so far. That is to say, things don't intersect, they occupy a fixed position, they don't move around. They have a discrete nature in a way, right? Our lattice gas model. The hard sphere gas model, on the other hand, which is the straight line, it seems to fit experimental data, which are the circles here, the best, where increasing hemoglobin concentration increases the osmotic pressure in a what looks like a quadratic curve upwards, with the hard sphere gas model fitting the data best. The lattice gas model, it appears, and the scaling factor here is just the factor of V. Yeah, you remember our assumption about the size of the volume of the molecule. It comes in the range, so 4V sort of comes close to what we're looking at, but it's not the same shape. It doesn't fit as elegantly as the hard sphere gas model. The hard sphere gas model, just to remind ourselves, is that two molecules are treated as spheres. They cannot pass through each other. They have volume interactions. That is to say, they at some point they repel each other. At a critical distance, they are able to stand close to each other, and this is a continuous model as opposed to our discrete lattice model. So this is sort of coming back to what I said earlier, which is that these models can be improved upon. The exact equation of the effect of hemoglobin on osmotic pressure is a little more complex, and it comes from a scaling of almost like a Taylor series of a factor x, which is nothing but 4 times the volume into the concentration of hemoglobin, where that volume is the volume of the hard sphere that we are assuming, and multiplied by kVt. So in that sense, this hard sphere gas model allows us to predict fairly reasonably well the effect of crowding on osmotic pressure. So, I mean, we've talked about macromolecular crowding, we've talked about the spacing, and we want to know maybe a little bit more about the cell line. So there, 10 to 100% of the fluid volume lies within 1 molecular diameter of the surface of the fibrous or membranous structures, and we have pores and we have reactants, and pore sizes are comparable. And just to remind you, the sieving effect that we saw might be explained by this kind of an idea, which is that as the size of a dextran molecule was increased on the x-axis, the relative offset in the cytoplasmic diffusion coefficient measured upon the pure water diffusion coefficient, the ratio, so to speak, changes such that it dramatically dips. In other words, the numerator reduces dramatically to go from 0.2 to 0.05 in the case of dextran at greater than 1,000 kilodaltons size. This does not necessarily apply as much to DNA because it scales differently, because you could say it's a polymer, and one can put a couple of proteins here in endogenous proteins to look at where this graph stands. But as I said earlier, also proteins, well, the answer depends. The sieving depends on exactly the size of the molecule. And so I'm going to move to the effect that we think might explain this kind of sieving effect, which is volume exclusion.